Welcome to the journey of exploring science and sleep, where the mysteries of the universe blend with the tranquility before you drift into dreams. Tonight, we will open the door to one of the greatest discoveries, the cosmic web, the immense and invisible skeleton supporting entire galaxies and superclusters. This is not only a magnificent tapestry woven from dark matter, but also the key to understanding how the universe exists and evolves. If you enjoy this journey, don't forget to subscribe to the channel and stay with us until the end of the video because the most wonderful secrets are waiting for you ahead. Imagine you are floating in infinite space, where every direction is an endless night. From that distance, galaxies scattered across the void look like shimmering specks of light, seemingly appearing at random in a vast dark ocean. But when science began to illuminate the grand picture of the universe, a miracle emerged. That randomness was only an illusion. Instead of chaos, the universe is woven into an incredibly intricate web. Invisible threads, mostly made of dark matter, stretch across billions of light years, forming a mysterious yet indispensable framework for the existence of every galaxy, star, and ultimately ourselves. The story of the cosmic web does not begin with brilliance, but with an unexpected stillness. After the Big Bang, when the universe was only a few minutes old, a dense mixture of elementary particles and energy rapidly expanded, leaving behind an almost flat and uniform canvas. By all rights, that explosive beginning should have carried chaos. Yet today's observations reveal that the early universe was almost perfectly smooth. Only the tiniest ripples in density, minute fluctuations invisible to the naked eye, broke that absolute uniformity. And within those faint ripples, the destiny of the entire universe was seated. When light first separated from matter, about 380,000 years after the Big Bang, a surprising trace remained that still exists today: the cosmic microwave background radiation. It is like a group photo of the infant universe, revealing slightly denser and slightly thinner regions in the primordial plasma ocean. The differences in temperature were less than 1 part in 100,000, yet they were the opening score to the entire cosmic symphony. Without those fragile fluctuations, not a single star would have ignited, not a single galaxy would have formed. All of it was possible only thanks to the patience of gravity. In the hundreds of millions of years that followed, the universe entered a phase called the Dark Ages. No light from stars or galaxies, only cold clouds of hydrogen and helium expanding with space. But beneath that veil of darkness, gravity worked silently. Slightly denser regions began to pull in more gas, slowly increasing their density. Meanwhile, areas with less matter grew thinner and emptier. Like a tiny crack on a sheet of winter ice, over time the initial small differences were amplified, paving the way for a greater structure to emerge. As time passed, the faint outlines of the early universe gradually became colossal filaments of matter. Under the pull of gravity, they drew material together at the intersections, which later blossomed into galaxy clusters and superclusters. Meanwhile, the vast empty spaces between them, called voids, became immense silent regions where almost no galaxies exist. When scientists mapped millions of galaxies in 3 dimensions, they recognized a familiar framework. The universe resembled a gigantic web, like an infinite spider's web stretched across the cosmos. But the strangest part is this: the web is largely made of dark matter, a substance invisible, non-luminous, emitting no electromagnetic radiation, and whose true nature we still do not understand. All we know is that it reveals itself through gravitational pull, as if invisible hands are holding galaxies in orbit, preventing them from scattering into the void. Without dark matter, the skeleton of the universe would collapse, and everything familiar to us, from starlight to planets, might never have had the chance to form. The image of the cosmic web not only astonishes astronomers, but also leaves ordinary people in awe of its delicacy. It is hard not to think of an exquisite woven tapestry where every tiny thread contributes to the greater picture. The universe is not random chaos, but a colossal design where order hides beneath apparent disorder. And in that contrast, we find a lesson. Sometimes, emptiness is not meaningless. It is the foundation upon which greater structures shine. Today, with modern telescopes and supercomputer simulations, humanity can partly reconstruct this web. The images are truly overwhelming. Billions of galaxies, arranged in long streams like rivers of light, intersecting at enormous nodes, while between them lie vast dark regions. Looking at those maps, one feels as though gazing upon the colossal brain of the universe, with eternal neural threads connecting everything together. Yet amid that grandeur, one cannot help but ask, how could such tiny early ripples give rise to such a complex structure? The answer lies in the persistence of gravity and time. Billions of years are no stranger to the universe. It works slowly, patiently, step by step, like an artist meticulously sculpting from invisible dust into galactic masterpieces. And on the largest scale, the cosmic web is precisely that sculpture, the silent monument of time and gravity. When you look at this web, you do not see only science, but also philosophy. It reminds us that the invisible is sometimes the most important, like the skeleton in a body unseen in daily life, but without it, every movement collapses. The universe is the same, and perhaps so is our own life. The idea of dark matter may sound like something out of a science fiction novel, but in fact, it was born from very real observations. In the 1930s, astronomer Fritz Zwicky noticed something strange while studying the Coma Cluster, a gigantic assembly containing thousands of galaxies. The galaxies in the cluster seemed to be moving too fast compared to the mass observed from the shining stars and gas. If only the gravity of visible matter were at play, the entire cluster should have flown apart long ago, yet they remained tightly bound. Zwicky put forward a bold hypothesis. There must exist some invisible form of matter with enormous mass holding them together. He called it dunkel materie, dark matter. Decades later, the evidence kept piling up. Vera Rubin, a persistent and intuitive astronomer, studied how stars orbit around the centers of spiral galaxies. According to Newtonian theory, stars at the edges of a galaxy should rotate more slowly, much like the outer planets of the solar system move more slowly than the inner ones. But her findings were astonishing. Stars on the edges rotated almost as fast as those near the center. The rotation curve of galaxies was flat instead of sloping downward. This could only happen if a massive invisible halo surrounded the galaxy, providing extra gravitational pull we could not see. These pieces of evidence, along with dozens of other studies, reinforced an undeniable truth. What our eyes and telescopes see is only a tiny fraction of reality. All the stars, planets, nebulae, and gas clouds, all the familiar luminous matter, make up only about 5% of the universe's total energy mass. The rest, around 27%, is dark matter, and the remaining 68% is dark energy, an even greater mystery. This means nearly the entire universe we live in is governed by invisible things, things that emit no light at all. In essence, we are living in a ghost universe, but this ghost is far from useless. On the contrary, it is the silent architect. Dark matter acts like a skeleton, pulling galaxies together, forming enormous chains and clusters. Imagine a gigantic spider's web where the invisible threads can only be felt through gravity. Along these filaments, galaxies form and cling like sparkling dewdrops. Without dark matter, those dewdrops would never cluster, but would scatter into the void. Supercomputer simulations have recreated this in spectacular fashion. When scientists input the right amount of dark matter into models of the early universe, filaments gradually emerged, galaxies formed in the correct places, and vast voids appeared exactly as we observe with telescopes. Without dark matter, the models immediately failed. Galaxies never coalesced into structures. This shows that dark matter may be invisible, but its footprints are everywhere. Ironically, despite knowing it exists, we still cannot see or touch a single dark matter particle. It does not interact with light, does not emit radio waves, does not reflect X-rays. It passes through you, through Earth, through the solar system as if we were not there. Physicists call it gravitational shadow. Only its gravitational influence can be measured. Many sophisticated experiments, from deep underground chambers to giant particle detectors, have been built to capture direct signs of dark matter. So far, no conclusive detection has been made. Dark matter continues to keep its secret. And here we stand before a beautiful paradox. Dark matter is something we cannot see or grasp, yet it is the foundation shaping everything we know. It is like an eternal background music. You never see it, but if it vanished, the entire cosmic performance would collapse. From this perspective, the night sky you gaze at is not just the brilliance of light, but also the silent symphony of darkness. When you look up at the Milky Way, the twinkling stars are only the surface of a much larger canvas. Behind that light, the universe's invisible skeleton silently supports it all. We may think we are seeing the complete picture, but in truth, we are only beholding a sketch. The painting itself is drawn in an ink that human eyes can never see. But perhaps that is what makes the story so captivating. The universe reminds us that there are vast truths beyond the reach of our senses, that even when we see only 5% of reality, the remaining 95% is still there, governing, shaping, and challenging our imagination. The cosmic web, with all its grandeur, is woven not only of light, but mostly of darkness. And within that contrast, the universe finds its beauty. In your imagination, you can think of the early universe as an almost empty canvas, dotted with just a few faint lines. But over time, that canvas was gradually sculpted by the most patient artist ever to exist: gravity. Tiny variations in density, seeded by quantum fluctuations in the very first moments after the Big Bang, were the initial sketches. Gravity is neither noisy nor hurried. It is like a background melody spanning billions of years, gentle yet persistent, guiding each particle of matter toward one another. Combined with the invisible skeleton provided by dark matter, this process led not only to the formation of gas clouds and solitary stars, but also to the creation of a vast web stretching across the cosmos, the cosmic web. What makes this process miraculous is not only the infinite patience of gravity, but also the way it chooses direction. Matter does not simply fall inward like a raindrop hitting the ground. It flows along invisible underground streams, forming giant sheets first, then gathering into filaments, and finally clumping into knots, where today we find the largest galaxy clusters. This asymmetry, which scientists call anisotropic collapse, is the very magic that shapes the universe's majestic architecture. If matter had collapsed uniformly, all we would see might just be a soulless scatter of galaxies, instead of the intricate cosmic highways stretching billions of light years. Supercomputer simulations give us the chance to watch this process as though rewinding history. By inputting fundamental physical laws and the conditions of the early universe, scientists observed an almost mesmerizing spectacle: tiny initial specks gradually stretching, linking, then extending into thread-like structures. They merged at intersections into bright, glowing nodes, while the gaps between filaments grew increasingly empty. After hundreds of millions of simulated years, the resulting image looked just like a 3D painting of a giant spider's web, none other than the cosmic web now recorded by modern telescopes. The match between simulation and observation is a beautiful proof that we are truly understanding how the universe sculpted itself. But that match also brings another overwhelming sensation: scale. Imagine, each strand of the web can stretch for hundreds of millions of light years. At such distances, even light, the fastest thing in the universe, would need hundreds of millions of years to travel from one end to the other. And yet these strands are anything but fragile. They are immense highways of hydrogen and helium, along which ordinary matter flows, gathering to ignite into stars and galaxies. If galaxies are like jewels, then the cosmic web is the delicate yet resilient thread stringing them together. What's astonishing is that this entire architectural masterpiece arose from initial density differences so tiny they are almost unimaginable. Just one part in 10,000 differences between regions, amplified by gravity over time, became the towering skyscrapers of the cosmos. In other words, if the early universe had been a little smoother or a little more chaotic, this entire web might never have existed. We, the small beings sitting here gazing at the sky, are in fact living in a lucky universe where a fragile balance allowed beauty to emerge from chaos. More than that, the cosmic web opens a new perspective on the very concept of empty space, because in reality, cosmic voids are not truly empty. They are painted by countless filaments of dark matter and by bent light. When telescopes observe a distant galaxy stretched into an arc by gravitational lensing, that is the moment we glimpse the invisible hand sketching the picture. By assembling millions of such fragments, scientists have drawn a three-dimensional map of the universe, and the result could not be more spectacular. Gigantic filaments interwoven, connecting everything from the tiniest star to the mightiest supercluster. One could say that the cosmic web is the background symphony of reality. The shining galaxies, stars exploding into supernovae, or planets orbiting around stars, are just the highlighted notes. The invisible skeleton is the main melody, slow but unending, resonating for 13.8 billion years. When we gaze at the night sky and see thousands of points of light, what we are truly witnessing is not just scattered lamps, but the final result of a song that began with the tiniest quantum fluctuations. The existence of this web is also a humbling reminder, because most of it comes from something we cannot see, dark matter. Everything our eyes perceive is just the surface decoration. But behind it, dark matter and gravity are the directors, the silent architects writing the script. The universe, in a sense, always contains more than what we can see, and it is precisely this hiddenness that makes it so captivating. If there is one lesson to take from this story, it is this: the smallest can lead to the greatest. Quantum fluctuations, vibrations so subtle they defy intuition, became the seeds of galaxies. Tiny density variations became the blueprint of the entire universe. And those invisible threads, though we cannot grasp them, are the skeleton holding reality together, making it a place where life and consciousness can exist. When we look up at the sky, we are not only looking at light, but also peering through history into the slender yet eternal filaments that have woven the greatest story of all, the story of the cosmic web. When we look deep into the knots of the cosmic web where the giant filaments intersect, we not only see dense galaxy clusters, but also cosmic stages where everything becomes most alive. There, thousands of galaxies crowd into what seems like a confined space, like a radiant city in the middle of a vast desert. Scientists call these galaxy clusters, the colossal fortresses of the universe where matter is compressed so tightly that the laws of physics reveal their strangest aspects. A single galaxy cluster can contain a mass thousands of times greater than the sun's, and its gravitational pull is so strong that even light is bent, turning the cluster into a natural telescope, magnifying the galaxies lying far behind it. Among them, the Coma cluster has become a prime example. Discovered more than a century ago, Coma looks like a gigantic cosmic beehive, where thousands of galaxies revolve around a shared gravitational center. From the perspective of a telescope, each galaxy resembles a bee, working tirelessly, colliding, merging, then separating in a chaotic yet ordered dance. They do not move freely at will, but are tightly bound by the gravity of the cluster, making the entire system an inseparable whole. Looking at it, we realize that the universe is not just a random mess. It is a web tied together by invisible but powerful strings. At the centers of clusters like Coma are often giant elliptical galaxies, solitary giants dominating their skies. They form from countless mergers spanning billions of years, as smaller galaxies are drawn along the filaments and fall into the center. This process is like a great city absorbing smaller towns around it, gradually expanding its reach and influence. Those central galaxies swell, shine brightly, and become the anchors that keep the cluster stable. When we observe them, we can imagine them as cosmic kings, surrounded by thousands of satellite galaxies spinning ceaselessly. Yet galaxy clusters are not merely lumps of stars and gas. They are also sites of extreme phenomena that few places in the universe can match. The gas between galaxies, compressed in this dense environment, is heated to tens of millions of degrees. At that temperature, it glows not in visible light but in X-rays, detectable only by space telescopes. Thanks to this, we can see images of massive hot gas lakes, enveloping the entire cluster like an invisible mist. Within this medium, galaxies no longer live in isolation. They collide, tear each other apart, steal gas, or merge completely. These collisions have shaped the evolution of galaxies, transforming them into strange forms that astronomers continue to study diligently. Imagine, a galaxy alone in the cosmic void would age quietly, gradually consuming its gas to form stars and then fade away. But a galaxy living in a cluster is completely different. It is surrounded, stretched, even stripped of its outer gas layers. Each time this happens, it changes not only in shape but also in fate. This harsh environment has created the enormous elliptical galaxies at the centers of clusters, colossal relics of countless mergers in the past. Even more remarkably, galaxy clusters rarely stand alone. They are connected to each other by filaments stretching hundreds of millions of light years, forming gigantic superclusters. Imagine a network of highways where each intersection is a great city and the main expressways are the cosmic filaments. This entire web stretches across the observable universe, forming a structure so orderly it seems almost surreal. And within this network, our Milky Way is just a tiny dot on the edge of a supercluster, the Virgo supercluster, and further still, part of the enormous structure called Laniakea. The name in Hawaiian means immense heaven, a reminder that our very home is just a small link in an infinite chain. The existence of these superclusters makes us rethink the concept of community. It is not only humans who live in cities, nations, and alliances. The universe also has a similar hierarchical structure. From a single star to a galaxy cluster, and finally to a supercluster, all are part of a natural order where gravity plays both architect and conductor. In this way, we can see the cosmic web as a grand version of what we know on Earth, only magnified billions upon billions of times. If we pause to reflect, we will see that this is truly astonishing. It all began from tiny quantum ripples in the Big Bang. Those microscopic fluctuations, amplified over billions of years, arranged themselves into the colossal order we now call the cosmic web. It is a story of patience and persistence, where the smallest things became the foundation for the greatest. And it is precisely thanks to that silent arrangement that our galaxy, our sun, and ultimately our life could exist. In this sense, the cosmic web is not just a physical structure. It is also a mirror, reminding us of connection. Each of us, each planet, each galaxy does not exist in isolation, but is part of a vast, woven fabric. And when we look up at the night sky, we are not only looking at distant points of light, but also at the very framework that supports reality, the invisible skeleton of the universe. The universe we live in is not a chaotic space where galaxies drift aimlessly, but a delicately arranged structure like a gigantic carpet woven from countless invisible threads. Those threads are the cosmic web, the immense framework that gives shape to everything that exists. When we look deeply at how these structures form, a magnificent picture gradually unfolds. The universe does not only contain stars, galaxies, and galaxy clusters, but all of them are connected within a hierarchical system, from small to large, from simple to complex, and from visible to invisible. At the first level, the tiny ripples of matter in the early universe gradually grew thanks to gravity. From faint fluctuations in the cosmic microwave background, the first galaxies eventually formed. But galaxies do not stand alone. They connect to form clusters, and clusters link into superclusters, regions of space spanning hundreds of millions of light years. When astronomers built three-dimensional maps, the image that appeared was not random scattering, but long, radiant filaments connecting giant knots. That shape reminded many of the neural network of the brain, as if the universe itself were a gigantic living being thinking in its own way. What makes this picture even more fascinating is its contrast. If the cosmic knots are bustling galactic cities, where thousands of galaxies gather, collide, merge, and burst with light, then the voids are like vast deserts. Their galaxies are lonely, like tiny oases in an endless sea of sand. A typical void can stretch tens of millions of light years, and the largest void ever recorded, the Boat's void, spans hundreds of millions of light years, almost entirely empty. The existence of these desolate regions emphasizes a truth. The architecture of the universe is defined not only by what exists, but also by what is absent. And it is thanks to these voids that the cosmic web stands out. Like lace, like sponges, or like music needing pauses to create melody, the universe also needs emptiness as a backdrop for presence. The filaments of dark matter stretch taut, clinging together, connecting galaxy clusters into a stable system. Though most of this structure is invisible, we can sense it through the effects of gravitational lensing. When light from distant galaxies is bent around massive invisible structures. Through redshift surveys, when light is stretched by the expansion of space, or through X-ray observations of superheated gas clouds within galaxy clusters. All of this data combines into the hidden map beneath the night sky. Strangely, that map carries a social quality that is hard to believe. Matter in the universe seems to dislike isolation. It prefers gathering, prefers connecting, prefers forming vibrant centers. Our Milky Way is no exception. It does not drift alone, but is a humble member of the local group linked with the Andromeda Galaxy and many smaller galaxies. This group belongs to the Virgo supercluster, and that supercluster itself lies within an even larger superstructure called Laniakea, meaning immense heaven. Realizing this, we cannot help but marvel. Even at the grandest scale, the universe reflects the desire for connection, just as humans seek each other to form communities. But this connectedness is not eternal. It is locked in a silent battle with a mysterious force, dark energy. While gravity pulls matter together, building knots and filaments, dark energy acts as an invisible hand trying to push everything apart, accelerating the expansion of the universe. At present, gravity is still strong enough to keep clusters and superclusters bound, turning them into secure anchors. But billions of years from now, when dark energy dominates, perhaps even those anchors will no longer hold. The image of the cosmic web will fade, leaving galaxies increasingly isolated in an endlessly expanding ocean of space. Nevertheless, when we look at the cosmic picture today, we see it still vibrant and full of energy. The luminous knots are where galaxies burst into storms of new stars, where collisions create even larger galaxies, where light takes billions of years to finally reach our eyes. In contrast, the voids are like quiet rooms, where lonely galaxies evolve slowly, preserving their rare uniqueness. These two extremes, bustling and silent, complement each other, creating a dance of presence and emptiness. When you look up at the night sky and see the tiny scattered points of light, remember that they are only the visible surface of the cosmic carpet. Most of the threads holding everything together, dark matter, remain hidden, impossible to see directly. It is precisely this that is the skeleton, the sturdy scaffolding for galaxies, clusters, and superclusters to cling to. This awareness makes us feel something deeply human. We too are but a speck of dust in that web, connected, supported, and never truly alone. For centuries, the starry sky has appeared before human eyes like a velvet cloth scattered with indefinite points of light. Galaxies, from our point of view, seem to be just random bright spots without order. But as technology advanced and human curiosity urged the drawing of increasingly detailed maps, a completely different picture gradually emerged. Instead of a scattered mixture, the universe revealed an intricate structure, luminous threads linking galaxies into chains, forming gigantic walls, leaving vast voids like bubbles in the cosmic fabric. This discovery did not come overnight, but was the result of decades of persistent labor. In the 1970s, pioneering projects such as the CFA Redshift Survey first introduced the idea that we could view the universe not only on the flat plane of the sky, but also in depth. As data accumulated, astronomers were astonished to realize that they were observing an entirely new architecture. The universe had structure, rhythms, and patterns rather than randomness. The early maps looked like gigantic coral, like branches stretching long, and immediately raised a great question: what created these shapes? The answer became clearer only when imaging technology and data processing entered the modern era. By the late 1990s, a revolutionary leap emerged: the Sloan Digital Sky Survey, SDSS. With a dedicated telescope located in New Mexico, SDSS not only observed a small patch of the sky, but scanned vast regions, recording millions of spectra and measuring the redshifts of countless galaxies. The result was the most detailed three-dimensional map ever created, a picture no longer vague but vivid enough to change how humanity envisions the universe. Imagine you're looking at a giant web, in which each radiant node is a cluster of galaxies, and between them lie immense dark expanses, cosmic voids spanning hundreds of millions of light years. The filaments stretch like blood vessels, connecting large and small structures. This is not only a scientific image, it is a work of art by nature. Many people, upon first seeing this visual model, compared it to a gigantic brain, where galaxies play the role of neurons connected by countless shining axons. From Sloan's data, humanity not only looked at the universe on a colossal scale, but also heard echoes of the past. By analyzing the distances between galaxies, scientists discovered faint ripples, remnants of sound waves that once propagated through hot plasma when the universe was young. These baryon acoustic oscillations became a cosmic ruler, allowing the measurement of space's expansion over time. This was a scientific goldmine. From the faint light of distant galaxies, we could read the billions-year-long history of the universe. However, light tells only part of the story. Another part lies in darkness, dark matter, which makes up most of the universe's mass but is completely invisible. How can we map what cannot be seen? The answer comes from ingenuity, gravitational lensing. When light from a distant galaxy passes through a region of space containing much dark matter, it is bent. By observing these tiny distortions, astronomers can infer the presence and structure of invisible masses. In other words, we see the wind through the way the trees sway, even though the wind itself is invisible. Another tool comes from even older light sources, quasars, brilliant cosmic lighthouses billions of light years away. When their light passes through the thin gas between galaxies, it records subtle absorption marks in the spectrum. Each absorption line is like a fingerprint, revealing the distribution of hydrogen on vast scales. This technique, called the Lyman alpha forest, allows reconstruction of the slender gaseous filaments interwoven between galaxies, the fragile threads of the cosmic web itself. When all these techniques are combined, redshift surveys, gravitational lensing, quasar spectrum analysis, we possess a multidimensional toolkit, each tool adding a different piece of the puzzle. Just as mapping Earth's terrain requires not only roads, but also elevation and rivers, mapping the universe also requires many layers of data to clarify structure. Step by step, the invisible becomes visible, and the vague becomes evidence. What makes these maps special is not only their overwhelming scale, but also the feeling that humanity has touched something beyond imagination. A single filament in the web can stretch 500 million light years. A void can swallow hundreds of galaxies like marbles in the palm of a hand. Compared to maps of Earth with its modest circumference of 40,000 kilometers, cosmic maps make us realize we live in an ocean of space so vast that everyday language cannot describe it. And it is at this point that science intersects with art. The visual images of the cosmic web are both mathematically rigorous and so beautiful that they inspire awe. They can evoke lace patterns, tree roots, blood vessels in the body, or the neural networks in the brain. Behind those shapes is gravity silently pulling threads of dark matter for billions of years. Yet the result resembles an artistic masterpiece no painter could reproduce. Looking at the cosmic web, we do not only see distant galaxies, we also see humanity's curiosity and creativity. From connecting faint points of light in the sky, we have built a gigantic map outlining the universe's invisible skeleton. And at every stage, from the CFA survey to Sloan and more modern projects, we take one more step in the journey of understanding that the universe is not chaotic. It has order, it has structure, and most importantly, we have the ability to discover it.